Okay, welcome back to our final discussion in this particular chapter on chemical structure and interatomic bonding. This will be our final topic area on atomic bonding in solids, or what we're going to be calling the primary interatomic bonds. So this will involve this. We'll wrap it up. And I've got two boards to show you and go over, and then after that we will start with a brand new chapter called Structure of Crystalline Solids, and we'll start that probably next week, so beginning of school. Okay, so in atomic bonding, atoms, obviously, as we said before, like to have balanced electrical charges or a net zero charge to them. And all chemical bonds, as we said, also involve the electrons. They're in the marketing business, the electron glue kind of a thing. The stickiness, whatever you want to call it, but electrons are the only thing involved in making these different bonds. Atoms are at their most stable state when they have no partially filled electron shells, or what we're calling orbitals. So they're all trying to be like the noble gases. So at any rate, they're going to do what they can to bond with other elements, other atoms. So there are three basic primary chemical bonds that we're going to discuss, and they are the covalent bond, the ionic bond, and the metallic bond. And in covalent bonding, the key word here is sharing. Okay, the atoms are actually sharing electrons. So it's when two or more elements share electrons, and each atom achieves a stable configuration, kind of like what I've shown down here with two hydrogen atoms. Of course, they only have one shell, that one S shell, but it takes two electrons. They only have one. So when you combine the two, they go together and they stabilize by sharing each other's electron to make them both stable. So that's an example of a covalent bond there. It is particularly, it occurs between two nonmetals, which again are over towards the right hand side, and involves similar net electronegativities. All right, so they're usually generally going to be gaining electrons, like they did here in this hydrogen bond here. And these covalent bonds can also occur either as elements or as compounds. Okay, so that is covalent sharing now of electrons. Now, covalent bonding, we're talking about a little more detail later on, way down the end of the summer session, involving polymers, because polymers use the covalent bonds when forming of these chains, these polymer chains, and each individual monomer is bonded together by covalent bonding. So we'll talk about that when we get there, but it'll be a while. Okay. Now, next type of primary bond is what we call the ionic, or that's the key word here, is transferring. We're actually transferring the electrons on these elements or these atoms, and it occurs between two charged particles, which basically invokes the electrostatic type forces between negative and positive. And in this case, instead of sharing, these electrons are completely transferred from one atom to the next atom, to the other atom. So it's a complete giving up, taking away or giving up, depending on which one you're at. And these take place between elements of highly different electronegativities. In other words, the far end of the spectrums from left to right on the periodic table of element, they take place between those elements where there's usually one element that has just maybe one electron in its outermost valency shell. Obviously, it doesn't want to try to gain all those other, the seven other, potential seven other electrons, it would prefer just to dump this one electron to somebody else, give it up, in other words. And so on the other end of that spectrum, you have elements like fluorine, probably the most electronegative of all elements. But at any rate, it has 7 in its outer shell, and it needs one more, and so it wants to try to gain, and so it'll easily take something. Or chlorine is a good example of that. So, okay, so it is losing or gaining electrons, which forms what we've called yesterday ions, and we know that electron deficient atoms are known as cations, okay, because they have a positive charge, whereas on the opposite spectrum you have anions, okay, and they're negatively charged. Okay, so those are the two ions working here, and it occurs again between metals and nonmetals, whereas again the covalent between two nonmetals. These ionic bonds occur between metals and nonmetals, and when naming these ionic compounds, the metal is always listed first. And my example here is sodium chloride. The sodium and the chloride, the sodium being the metal, and sodium has only, in its outermost shell, only has one electron, and chlorine needs only one electron. So obviously, the sodium gives it up, and the chlorine takes away, and they're both happy, and both have a stable outer valency shell taking place. Okay, so that's the basics for ionic transferring of the electrons. Okay, so now let's bring the other board up here. Move this out of the way carefully, and bring the next board up. Put it into position. It's situated so that you can see it all here. All right. Making final adjustments. All right, so this looks like that's pretty much in focus with everything. Okay, so, and again, this is the last board, the 1D of these. And we're going to talk about metallic bonds. Now, the key word here, metallic bonds, is a pool, and there's many terms here you could use, a pool of electrons, sea of electrons, cloud of electrons, even a matrix, more or less, of electrons involved in metallic bonds. Now, metals have relatively few electrons in their valence shells. As such, we just talked about sodium. And so they cannot complete their outermost shells with other atoms because they just don't have enough to do that. And so what happens is they kind of pool all of their electrons together, and these valence electrons leave the individual atoms to become part of what we're calling a common electron cloud, or electron matrix, if you have that way. But and so then they have a much more range of this electronegativity. We don't have all these positive nucleuses there, and then now we have an electron cloud surrounding them. So it's a very, very, very strong bond going on here. Now, because they have all of these electrons in what we call a cloud or a matrix, it produces a considerable, what we call electron mobility within the atomic structure, and that yields two very important properties that you'll know, obviously aware of in metals, and that is conductivity. Both heat or thermal conductivity and electrical conductivity are a direct result of these electrons in this cloud, where they can move about and touch and regardless. So that's a very, very important properties that are, again, based upon this type of a bond with all of these electrons. And I've kind of shown here an electron matrix of a metal atom, where these circles here and these kind of look like lattice sites here. These circles here are the actual atoms, and then in between are all these given up electrons in what we're calling the electron matrix, or this cloud. So you can see they're very mobile in here, and the atoms are free to move about, so to speak. The volume within the volume of this between all these atoms, and it is also because of this property that these electrons are inside there and can move around. This arrangement also makes it possible for the atoms to slide past each other while maintaining its structural integrity. So that's the essence or the background on how metals can deform, and how deformation can take place. Because we know we can take a piece of metal and bend it and it won't break; it'll just deform. And there's two types of deformation from your solids days. That there are two types. There's elastic and plastic deformation. Elastic deformation is when you take something and bend it and then let go and it goes back. But again, it's all predicated on this sea or pool or matrix of electrons floating around here in this structure of a metal. Or you have plastic deformation where you bend it far enough and then it stays put. Okay, so at any rate, and it's all again based upon this property of deformation, based upon these electron matrices taking place there. And so, to sum it up, metals are solids composed of atoms held together by a matrix of electrons. And the electrons, again, are free to move about the volume of that atomic structure. Now, what we're going to call that, we're going to refer to that, are crystalline structures. And all metals have a crystalline structure. And we're going to get into a great detail about crystalline structures starting next week. On actually Tuesday or Monday, whenever you see this, involving the structure of crystalline solids. And we'll spend quite a bit of time on that particular subject area because it's critical to the understanding of how these metals and these solids react and what their resultant properties are. Okay, very, very based upon their crystalline structures. So this is an important point here, that when you classify, or the classification of solids, you can do it one or two ways. You can either do it by their bonding type, which we've done here as far as the covalent. Well, the covalent is not necessarily, well, covalent is solid, not a metal, but covalent bonding, ionic bonding, and now metallic bonding. So that's one way to classify solids based upon the bonding type. The next type is what's called the atomic arrangement. That is that crystalline structure. That's exactly what we're referring to, the atomic arrangement, and we can show how we can classify those based upon that particular atomic arrangement, be it ordered or disordered. So we'll get into the details of that next week. And last thing I kind of wanted to share with you right quick, we were talking about Mendeleev yesterday, and I wanted to show you this book that I have that is a quite fascinating read. And it's called Mendeleev's Dream, all right? His quest for the elements and the discovery of the periodic table of elements. A very, very nice book, very readable, especially if you're kind of into this a little bit. Very interesting accounts of what took place, how it took place, and what it yielded. So a great book if you're interested. And again, it's called Mendeleev's Dream, The Quest for the Elements, written by Paul Strathern. Okay, so we will terminate this and get started back on Monday. See you then.